Welcome back, students. In this video, we are going to continue a discussion on resistance, resistivity, and the temperature dependence of resistance. Okay, we'll start with Ohm's law, a discussion on Ohm's law. So, what does Ohm's law say? It says that the voltage across a conductor is proportional to the current flowing through the conductor. Okay? So this finally translates to V is equal to IR, where R is a constant of this proportionality. So this equation tells you that you have a linear relationship between voltage and current. It's a straight line. That's what you get from here. Because V is equal to IR, where R is going to remain the slope of it, right? But that is not the case, basically. Okay, when you actually even it's working okay over a range of voltages, but as you keep increasing the voltage, then you don't really get a linear relationship. The relationship is slightly off linear. So limitations of Ohm's law. That is the Ohm's law. So as per Ohm's law, you are supposed to get a linear relationship. Suppose if I have this is I, and then this is V, and then we expect it to be a straight line. Okay. So delta V by delta I should give you this R. But when you do it, when you actually do experiments, then you are going to be any conductor, it's going to be slightly off. Okay. So it's not a straight line, then it's actually a curve. So this is what we find. But then within a limited range, you notice here, then you can use this law. V is equal to IR. Within a certain range of currents, then you can treat this curve as a straight line. So Ohm's law works for the most part, but then we don't have a strict adherence to this law when we use conductors. So that is one of the limitations of Ohm's law. This is what happens in the case of conductors. And then there's a type of materials called as semiconductors. Okay, we know of conductors and we also know of insulators. These are the things that you are familiar with. But then there is a third type of materials which are called as semiconductors. You will be studying about them in your 14th lesson. So we'll be studying in detail about them later. But for the time being, just accept what I'm saying. Okay? You will actually understand it fully when we discuss semiconductors later. But for the time being, just accept what I'm saying at its face value. Okay? In the case of semiconductors, that is, Ohm's law is not obeyed. For example, so this is conductors, in the case of conductors. And when I take semiconductors, a different type of materials, okay. See, the resistance depends on the direction in which you connect the battery. Okay. Suppose there is a semiconductor, let's say. Okay. This is a semiconductor. If you connect battery in this way, I'm going to get a certain resistance. And if I connect battery in this way, opposite way, then I'll get a different resistance there. Okay? So we call that as forward bias and reverse bias. So all that we'll study later, as I said, but right now understand that in the case of semiconductors, this is not Ohm's law is not obeyed. Okay? So in the forward bias condition, and when I have a certain voltage here, voltage I keep increasing the voltage, then this is a current, it's going to be in milliamperes here. Okay, so after, if it is a silicon diode or something, then you will have, the current won't start over for a certain amount of voltage, for 0.7 till 0.7. Suppose you are varying the voltage from 0 to some value. So 0.1 you won't get any current, 0.2 you won't get any current, and 0.7 is a voltage which starts conducting. Okay, and then it's like this. Current suddenly increases. You see, you don't see Ohm's law being obeyed here in this range. Okay, and when you do the reverse bias, when you connect the battery in opposite direction, then what happens is current is not conducted for a very for a big value of voltage, and after that, when suddenly it starts conducting like this. We call it as a breakdown. Okay, so this conduction, or you can say a very slight amount of current is being conducted. So this conductor would be in microamperes. Same. So this is in milliamperes. This will be in microamperes. You see, this curve is not the same as this curve, right? It will never happen. For example, if I continue, you can expect it to go like this, right? The current to travel in the opposite direction, will change the voltage. So it still looks like a straight line in the case of conductor. But if you take semiconductors, you see the curve is something like this. So this expression, this relationship is not obeyed in the case of semiconductors. Then there are certain other types of conductors like gallium arsenide, where you don't have a unique voltage for a conductor, for an amount of current. See, that graph looks something like this. Like you keep increasing the current, when you keep measuring the voltage here, notice here that it is like this. You get a curve like this. Notice, for this voltage, you get this current. And then for the same voltage here, you get this current. So you have a dual value of current for the same amount of voltage. So you can see that as I increase the current, then the voltage across the material increases, and as I keep increasing the current, then suddenly the voltage starts dropping across the material. So they exhibit this type of characteristics too. So these an example of such a material is Ga, gallium arsenide. Gallium arsenide exhibits this kind of characteristics, and there are many special materials like this, and these materials, these substances are used more in electronic circuits along with semiconductors and stuff. Okay, so this is one of the instances where Ohm's law is not obeyed. So even though we say that voltage is proportional to current, which is fairly okay in the case of conductors, even though the Ohm's law is not strictly obeyed, it definitely is not obeyed in the case of semiconductors and materials like special materials like gallium arsenide, where you have a dual thing. Okay. So Ohm's law is a good law. It's a good practical law, and it gets us through a lot of problems. But then it is not a complete law. Not all materials obey Ohm's law. So even materials which are supposed to obey Ohm's law, like conductors, don't obey Ohm's law very strictly. Okay? So these are the limitations of Ohm's law. Hope it's clear. Okay, now let's talk about the resistivity. Okay, we derived this expression for resistivity, which is rho is equal to m by neat, right? or m by n e squared tau, where m is the mass of the electron and n is the number of free electrons per unit volume of the material, and then E is a charge on the electron, which is 1.6 × 10 − 19 coulomb, so that's E square now, and then tau, that is actually the relaxation time, that is the time between collisions. Okay. So this is what we derived for resistivity. And resistivity is related to resistance in this way. This you know already. So resistance is equal to rho to L by A. So this is ohm, so rho, and this is meter, and A is meter square. So this is rho by M is equal to ohm. So ohm is actually, rho is actually ohm meter. So the unit of resistivity is ohm meter. Okay. So we know this, and you can see that rho is not a constant value. It cannot remain a constant value for a material. So because rho depends on tau. M is constant anyway, E is constant anyway, N is also constant for a material. If it is copper, then you will have one value. If it's aluminum, you will have a different value, and so on. And tau, even in a single material, is not a constant value, because tau, as I said, is a collision, the time between collisions, the relaxation time. So if the electrons move fast inside the conductor, then it can increase the number of collisions per time, meaning that the time per collision reduces basically. Okay, so if tau reduces, that means that electrons are moving very fast, which will be the case when the temperature of the material increases, and because tau decreases, then rho will increase. So the temperature increases, tau will decrease, and rho will increase for the same material. So whenever we talk of rho, we'll talk of rho at a particular temperature or within a range of, you will assume rho to remain constant over a range of temperature also. Okay, so this is what we would assume. So you need to understand that rho is not constant for a material. Rho can change because tau can change. The relaxation time can change because of temperature. As temperature increases, electrons move faster, thereby reducing the relaxation time. If rho reduces, then rho increases. Okay? And you have a table in your textbook that gives you the rho value for different elements, for silver and for copper and gold and all that. Okay? It's given. So you can go through that and figure out and for yourself what rho value is for different materials. Okay, it's there in your textbook. And you can also see that the rho is defined for a particular temperature. In this case, it is 0 degree Celsius. Okay, so they've defined rho for silver 0 degree Celsius. Okay, so it's there in the table. You can go through the table. So now that we've talked about it, we'll talk about what is called as the carbon resistors. Okay, so carbon resistors are like this. This is a resistor actually. I don't know how well you can see it. I'll probably have a closer look at this with the camera, or even I can take a picture and then add to this video. So this is a carbon resistor. Actually, I've cut this wire here. There's a wire like this here too. Okay, it's a carbon resistor, and this resistor has rings around it. I'm not sure if you can see it. If you don't see it, don't worry, I'll show it again. So this has rings around it, different color rings. Actually, those rings give you the value of the resistance. Okay, We'll talk about how to figure out those values and stuff. First of all, if you take this resistor, carbon resistor, okay, let's say this is resistor, then you have 3 lines here. Okay, 3 lines here and then 1 line here. Okay, so these 2 lines are actually, the first 2 lines are the resistance, the significant digits actually. Okay, these are significant, these are the numbers which are significant. And then the third one is called as a multiplier. Okay, and the fourth one is the tolerance. The 4 lines will be drawn. So there are 2 lines which are significant, and then there is a multiplier, and then there is this tolerance level. Okay, they are different. They are in different colors, and each color stands for a number. Okay, for example, black stands for 0, and brown stands for 1, and red stands for 2, orange stands for 3, yellow stands for 4, green stands for 5, blue stands for 6, violet stands for 7, and then grey stands for 8, white stands for 9. Okay, so these are the 10 digits actually represented by these colors. Okay, and then for tolerance you have gold. So the fourth, gold, which means it's 5% tolerance, and then silver means 10% tolerance, and no color, no ring. Okay, no ring, that is 20% tolerance. So what it means is that if you have a gold ring here, gold line here, then that is, I have 5% tolerance. I'll tell you what it is a little later. To understand that if you have a gold line here, then it's 5% tolerance, and then silver line is 10% tolerance, and then there is no line here at all, no ring drawn here. That means that's 20% tolerance. It just talks about the quality with which the resistor has been made. We will come to that later. So these are basically the colors which are involved in it. And how do you remember this? So I'm going to take the first ones, first letters. Okay. So the sentence that's going to help you remember this is this: B.B. Roy of Great Britain had a very good wife. Okay, it says B.B. Roy of Great Britain, okay, had a very good wife. Okay. So if you remember this, then you should be able to reproduce these values. Okay. So B.B. Roy of Great Britain had a very good wife. B, first is black, second B is brown, and then or red, O is orange, Y is yellow, and then green is 5, B is blue, and then violet 7, and then very is violet, and then good is gray here, and then white is white here. Okay. So you should be able to recreate these numbers very quickly. Okay. So I will tell you like how to calculate the resistance a little later, but I want you to understand this. So if you remember this sentence, B.B. Roy of Great Britain had a very good wife, then you should be able to get the numbers for these colors. Well, in the process, you may have a difficulty. You see, you have 1, 2, 3 B's, and then you have 2 G's. Okay. How do you remember? Which is whether it is the first one is black or brown or blue? How do you remember that order? Okay. For that, you can use your own uniform. Okay. So you have you have blue, you have red shirt and then check shirt, and then you have a blue coat, overcoat on it, right? Now you remember that you being in your uniform. First, it's black hair, and then brown your face, and then blue jacket. So black, brown is your face, and blue jacket. So black, brown, and then blue. So there can be no confusion there. So for that you need to remember your friend in uniform or yourself in uniform. Hair black, face brown, blue overcoat. So that is order in which the B's appear in this sentence. Okay. Next one, GG, great and good. So one is green and then the other one is gray. So how do you remember that? It's a question. For that, okay, you imagine a tree or a plant. Okay. So what do you have on the top? You have this tree, let's say. Okay. So this is green, right? This is green. And here, maybe the gray soil is gray, something. So the tree, the top of the tree is green, and then the bottom is gray. So that is exactly what you're doing. First you get green, and then you get gray. So if you know this, then you have mastered the colors in this used in specifying the resistance on a carbon resistor like this. Okay. Let's say now the first two digits are significant digits, right? So sorry, the first two yeah. Are this. Suppose, like, let me take this one. I have brown, black, and silver here. I have brown, and then brown, and then black, and then silver. These are the things I have in this. So let me try to calculate the resistance of this. Okay, first one, what's the value of brown? First one is brown. Brown is 1. Next is again brown, 1. Third is black. Okay. Third is black. So that is actually, I said it's a multiplier. Third is a multiplier. You need to worry only about the first two, and the third one is actually a multiplier. So 11 into 10 to the power, what is black? Black is 0. So 10 to the power 0 is 1. 1 into 11 is 11. So it is 11 ohms. So what is the value of resistance here? I have a brown here, I have another brown here. Brown is 1, brown is 1. So 1, 1. That is significant difference. And the next one is multiplier. That is 10 to the power this color. 10 is small. Because I got black here, I am going to put 0 here. Suppose I have brown again, then that would become 10 power 110. So it will become 110 ohms. But I have black only. So since I have black only, so it becomes 10 power 0. Suppose I had green here instead of black, then what would happen? 11 into 10 to the power, green value is 5, 10 to the power 5. Okay. It's going to be 1100 kilo ohms. Okay, so it's 10 to the power 5. But in this case, this resistor I have has brown, brown and black. So 1, 1, significant, 11 into 10 to the power black. Okay, it's a multiplier. That's why you call the third one as a multiplier. It's a 10 power. So you multiply this color with this color. But you don't straight away multiply it. You raise it, you raise 10 to the power of the color and multiply that value with these two. Okay? So I get 11 ohms in this. Then what about this tolerance level? Silver. I said silver will have 10% tolerance. What does it mean? The silver has 10% tolerance. It's plus or minus 10%. That's what it is. So it talks about the quality with which this is made. Okay, if it is made with very high quality, see, nobody can make exactly 11 ohms. It's difficult to make exactly 11 ohms. There will be some changes, right? Nothing can be perfect. So what they say here is that, yeah, our rating is 11 ohms, but it can vary within 10% of the stated figure. So 10% of 11 is 1.1 ohm, right? So this is 10% of 11 is 1.1 ohm. So the actual resistance could be anything between, okay, 11 is 10, 9.9, 9.9 to 12.1 ohm. Okay. So they say this, our stated resistance is 11 ohms, alright, but then it isn't made with 10% tolerance, which means that even though we say that it is 11 ohms, the resistance could be anywhere between 9.9 and 12.1 ohms. It's within that range. Well, it can still be 11, it can be perfectly 11 or 11.1, or it can even be 10 ohms or 10.5 ohms. Okay, as long as but what is assured, what is guaranteed to you is this. Well, we say that it is 11 ohms with 10% tolerance, meaning that this resistance will be anything between these two values. Okay, so if it is, suppose if it had gold lying here, then it would have been only 5% variation, meaning that if I multiply it with this one, it is going to be 0.55. So I can add and subtract 0.55 to it, this 11 ohms. So it can be 11.55 on the higher side or 10.45 on the lower side. So if I had a golden line here, same 11 ohms is a stated resistance, but then that can vary between 10.45 and 11.55. So you see, you have better quality there. The quality control. This is an indication of the quality control that they have had while manufacturing this resistance. Okay. So I hope this is clear to you. So we are talking about the rating on the carbon resistors. This is a carbon resistor. Okay, it's going to be used in circuits, electronic circuits. You can find something like this quite often. If you open up a box of an electronic instrument, then you will find things like this. This is actually a resistor, a carbon resistor, and then the lines, the rings on this, they call these things as bands also. Okay, have different colors. There are 4 rings on every resistor. 3 to 4. Okay, 3 rings are a must. The significant digits and also the multiplier. This is a must. If we don't have the 4th ring, it means that it's of lesser quality, because the tolerance is 20%. So it can vary. Even though I say 11, it can vary 20% this side or 20% that side. Okay, so 2.2 ohms less or 2.2 ohms more. Okay, so it can be it's 2.2 less, then it will be 8.8 ohms on the lower side and 13.2 ohms on the higher side, if there was no line here. So you have a golden line, which means that this is of a very high quality. The tolerance level is only 5%. The actual value is going to change. We say that the value is 11 ohms, but the actual value is going to change only within 5% of this stated value. Okay? So that is the meaning of this. So remember this, B.B. Roy of Great Britain had a very good wife, and start with 0, then you will have this. But then the B.B. Roy of Great Britain had a very good wife, had 3 B's and 2 G's. The way to remember the 3 B's, the order in which they appear in the sentence is your own uniform. Okay, you have black hair, brown face, and blue coat. So that is the order in which the B's appear in this sentence. And for the G's, you need to think of a plant. Green on the top and grey on the bottom. So first is green, second one is grey, the grey floor, green leaves. Okay. So once you know this, then you should be able to figure out what each color stands for, the number each color stands for. And you need to take the first 2 digits, the first 2 colors, and to figure out first 2 digits. You put them together like this. Okay. And then the third one is a multiplier. I mean, you are not going to take the third one straight away multiply this number. You are going to take the third one and raise 10 to that power and then multiply. And you get this one. And then the fourth one tells you the tolerance level. This is the resistance area. This is the stated resistance. The manufacturer says that this is it. I mean, it's 11 ohms. That's what he says. But then he also says that within 10% of tolerance. When I say that it is 11 ohms, it can be 10% on the lower side or 10% on the higher side, or any value in between. The maximum is 10%. The maximum variation is 10% on this one, on this side, and 10% on the other side. But if I had used a golden ring, then it's only 5%, so better quality control. And if there is no line there, then it is 20%. It can vary 20% on this side and 20% on that side of this value, 11. Okay. So poor quality control. I should say poorer quality control compared to the other two. I hope this is clear to you. Okay, the next topic that we would take up is a temperature dependence of resistivity. We just talked about it before, and then I will expand on it. So temperature dependence of resistivity. We talked about it, right? So rho is equal to m by neat. Okay. We said as the temperature increases, tau will become smaller because the relaxation time will become smaller because the electrons will move faster and the collisions will happen quickly. So tau will be smaller, so rho will become higher. So the resistivity increases with temperature. Okay? If you let's see at some temperature T, at some temperature say T equal to T naught, you had a particular rho. I'll call it as rho naught for the material. So let's say you have copper, and for copper you have at some temperature T naught, you have this resistivity rho naught. And when temperature rises to say T1, and let's say you have the resistivity rose to rho 1. So maybe it was say, I will have just putting it, maybe it's some rho naught ohm meter, it has become rho 1 ohm meter. Okay, that is, these are the two resistivities at two different temperatures. So we can see that if T1 is greater than T naught, clearly, okay, so if T1 is greater than T naught, then what does it mean? It means that rho 1 must be greater than rho naught, right? Whereas the temperature increases, the resistivity should also increase. So I can say that rho 1 can be written as rho naught plus some change in resistivity. Right? So rho 1 is greater than rho naught, so I can say that this is rho 1 can be written as rho naught plus delta rho. That's a change in this. Suppose if this suppose this is rho naught plus 10, and let's say if this is 15 now, rho naught plus 10 and rho 1 is 15, then delta rho is actually 5. So that's a change in resistivity. Okay. This change in resistivity, this delta rho, is definitely proportional to change in temperature, right? Because the temperature changed, so you have this. Okay, that is there. It's definitely proportional to the change in temperature. And it is also proportional to the material, the type of material. Okay. For example, if it is copper, then delta rho will be some value. If it is iron, then delta rho will be a different value for the same change in temperature. Let's say I go from 100 degrees to 120 degrees. So the change is 20 degrees, okay, temperature. But if I had copper, then that will have one delta rho, and if I had iron, it will have a different delta rho. And if I had aluminum, then it would have yet another delta rho. So even though the temperature change remains the same, delta rho will not remain the same for these materials. So depending on the material, the delta rho will change. Understand? But then rho naught is also dependent on the material, right? That's what we saw. Rho depends on like N and 2. Because M and E are the same for all materials. That's simply mass of electron and charge of electron. They will remain the same for all materials, whether it's iron or gold or copper. But where will the difference be? The difference will be in N, which is the number of free electrons per unit volume, and then tau, the relaxation time, the time between collisions. Only here that could be changed, and that depends on the material, right? So rho depends on the material, and now delta rho also depends on the material. So I can say that rho depends, the delta rho depends on rho naught. Material. Whatever rho you have, delta rho depends on that too. Okay? So if it is copper, then you would have a different rho naught at this temperature. And then if it is iron, it would be something else, right? So delta rho is proportional to delta T, the change in temperature. Clearly, all materials will have a different resistivity when the temperature changes. So delta rho will be dependent on delta T temperature, and also is dependent on rho naught, the initial whatever resistivity you have right now. That depends on the material. Okay. So if I combine this, then I have this delta rho can be written as I can introduce a constant of proportionality, which I will call as alpha. Okay, and then rho naught and delta T. Okay. So this is proportional. This is alpha. Okay. They are different. They are two different symbols. This is a constant. This is just a proportionality symbol I have here. So delta rho is equal to alpha rho naught to delta T. Well, if we take this and put it in this equation, what I'm going to get now? Now rho 1 is equal to rho naught plus alpha rho naught delta T. So what is delta T? So delta T is simply T1 minus T0. Final temperature minus initial temperature, that is delta T. So I get that. So I can take rho naught out. I'll have 1 plus alpha delta T. That's my rho 1. So if I know rho naught at a particular temperature T naught, I can calculate rho 1 at a different temperature if I know alpha. If I know this constant, if I know this value, alpha value, then I should be able to calculate it. Okay? Again, this alpha also depends on temperature. Okay? And this is also listed in the table that I just talked about, the table that has resistivity. In the table you also have alpha, okay, for different materials at 0 degree Celsius. So it's not linear, it's linear only, so over a very small temperature range. Anyway, so this is the expression, you need to remember this expression, that's the expression that helps you figure out what your resistivity will be at a higher or a lower temperature when you know the resistivity at one temperature, provided you know alpha in that range. Okay. So this is a very important idea, and if you know rho, then naturally, since rho is simply rho L by A is R, then resistance also can be written like this. So rho 1 will become R1 equal to R naught to 1 plus alpha delta T. Okay, this is also alpha. So this expression is for rho, resistivity, but once you know resistivity, you can find resistance by simply multiplying the length and then the area, multiplying the length and dividing it by the area of the conductor. You should be able to find out. So resistance also will follow the same pattern. This is for resistivity, this is for resistance. Similar. And what is the unit for alpha? Well, I can do it from here. Right? I can do it from here. So delta rho is equal to alpha rho naught delta T, right? Alpha. This alpha is called as temperature coefficient of resistance or resistivity. Okay, it's alpha is temperature coefficient of resistivity. Okay. And what's its unit? This unit I can get from here, right? So delta rho is equal to alpha to rho naught into delta T. So delta rho unit is ohm meter, okay, and alpha, and the rho naught unit ohm meter, and the delta T temperature unit will be degree centigrade or Kelvin, doesn't matter. Okay, so now, so ohm will cancel, meter will cancel, so alpha is equal to, unit of alpha is actually per degree Celsius. Okay, it's like degree Celsius minus 1, because it will come here, so it will be 1 by degree Celsius, so degree Celsius minus 1. So that will be unit of this temperature coefficient of resistivity. Okay. So I hope this is clear to you, and then we'll talk about the temperature, the resistivity graphs of some of the materials, and then we'll do a problem. We'll draw 3 graphs now. One is the resistivity graph as a function of time, temperature for copper. Okay, so it is something like this. So copper, okay, rho on this side, and this is in 10 to the power minus 8 ohm meter. That's a unit here, 10 to the power minus 8 ohm meter, and this is in temperature is in Kelvin. Okay, so what happens is you have 50, 100, I'll say this is 50, 100, and 150 is here, and then you have 0.2 and then 0.4 here, 0.2 and 0.4 here. So it starts, the graph is like this. Or I should say, something like this. Okay, this is 50 Kelvin, 100 Kelvin, and 150 Kelvin. So you can find resistivity at different temperature. You see, resistivity is not constant. As temperature increases, the resistivity itself changes. So resistance of the material would change. Okay, it won't remain constant. Anyway, so this is for copper. This is graph number 1. And the second graph is for a material called nichrome. Okay, nichrome is an alloy of nickel and chromium. It is used in circuits because the resistivity changes very slightly over a wide range of temperature. So that's a great advantage because the resistance will not change. The resistance doesn't change for an applied voltage. The current will not change over a wide range of temperature. So you can expect some stability. Okay, so when you say this material has certain resistance, this piece has certain resistance, then that resistance will be the same over a wide range of temperatures. So materials like nichrome, constantan, manganese, these have almost constant resistivity. They are not exactly constant. The resistivity varies very slowly with respect to temperature. But you can't say the same thing about copper. You see, it changes a lot from 0.2 to 0.4. It becomes double over 100 Kelvin. it has become double or 100 Kelvin. But then if you take Nichrome, it is something like this. So I have 200, 400, 600, 800 Kelvin. Okay, temperature here, again in Kelvin. Okay, and then again resistivity rho here. So it's micro ohm centimeter. It is micro ohm centimeter here. Okay, it is so small, micro ohm centimeter. You see here I got 1.1, and then here I got 1.2, something like this. This is 1, let's say I start with 1, 1.0, 1.1, 1.2. Then notice here, from here, you see, the graph is like this, rho is like this. Notice here, over a range of 800 Kelvin, it changes only 10%. Okay, the 0.1 is a change. But here notice, over temperature difference of 100 Kelvin, it doubled from 0.2, it became 0.4. It doubled, copper doubled. But here there is 100% change in this range. But here, notice, it is over a temperature of 800 Kelvin, only 10% change. So the resistance will remain almost constant over a wide range of temperature. So increasing temperature doesn't really change the resistance of these materials. And these materials are going to be used in instruments like meter bridge and potentiometer, and those are things that will come again. You will come across. They are used in electrical instruments where you want resistance to remain pretty much the same. Okay, so this is for Nichrome. Okay. And then for semiconductors, I said, semiconductors, the resistance will decrease. The resistance will decrease with the rise in temperature. You will know why it happens, but then for semiconductors, as temperature rises, resistivity will fall like that. So that's because of temperature, the electrons will be released in silicon, and then they'll start conducting. So, but that's for lesson number 14. But for the time being, you understand that for semiconductors, when the temperature increases, the resistivity will come down. But for conductors, typically as temperature increases, the resistivity increases. How much it increases depends on the material used. As we saw here in copper, in a very small range, 100 to 150, the 50 Kelvin change, 50 degree change resulted in 100% change in resistance. But here in Nichrome, over 800 Kelvin, the change in resistivity was only 10%. So these materials are very important. They have a special purpose. Okay, where the resistivity doesn't change or remain approximately the same over a wide range of temperatures. In the case of semiconductors, the resistivity will decrease as you increase the temperature. Okay. Hope this is clear to you. Okay. Let's do example 3.3. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature, which is 27 degrees Celsius, is found to be 75.3 ohms. When the toaster is connected to a 230 volt supply, the current settles after a few seconds to a steady value of 2.68 amperes. What is the steady temperature of the nichrome element? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 power minus 4 per degree Celsius. Okay. So what is happening? First of all, you have a heating element, an electric toaster that has a heating element. It's a nichrome heating element. So when a negligibly small current flows through it, which means that like it's not going to heat it up. Okay. At room temperature, it is found, the resistance is found to be 75.3 ohms. Let's say R0 at room temperature is found to be 75.3 ohms. That's the resistance of, example 3.3. That's the resistance of the heating element. So when the toaster is connected to a 230 volt supply, the current settles after a few seconds to a steady value of 2.68 amperes. So voltage applied, this is a heating element, let's say it's a heating element. Okay, it's a heating element. You are applying a voltage across this. That is 220 volts. 230 volts. So 230 volts is what you apply. And once you apply this, then the current settles at 2.68 amperes. 2.68 ampere current is flowing through it. Then the question is, what is the steady temperature of the nichrome element? So what is the temperature of this? Well, at room temperature it had 75.3 ohms. Now 2.68 ampere is flowing through it. Then what must be the temperature of this element? That's the question. To do that, first of all, you need to find the resistance of it, right? Okay. So I have 230 volts and 2.68 amperes. Then what is the new resistance of it? It's going to be equal to V by I. So that is 230 by 2.68 amperes. So that gives me 85.8 ohms. So this element had a resistance of 75.3 ohms at room temperature, which is 27 degrees Celsius, and now it has a different resistance of 85.8 ohms because now it is at a different temperature, right? It's a heating element, and then it heats things up, and there is temperature change that has happened, and at that temperature the resistance is 85.8 ohms. Now the question is, what is the temperature of the heating element? Okay, so how do you do that? Okay, we know this. What is it? So R1 is equal to R0 into 1 plus alpha into delta T. So delta T is a change in temperature, and alpha is the temperature coefficient of resistance in this range. They are given it, right? So they say this: the temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 to the power minus 4 per degree Celsius. So alpha here is 1.7 into 10 to the power minus 4 per degree Celsius. Okay, alpha is given. So you know R1, you know R0, then let's find out delta T. So what is R1? R1 is 85.8 ohms, equal to R0 is 75.3 ohms, and then from 75.3 it has become 85.8 because of this 1 plus 1.7 into 10 power minus 4 into delta T. Okay, so what can we do now? We can take this, right? So 85.8 by 75.3 is equal to 1 plus 1.7 10 to the power minus 4 delta T. So from here 85.8 by 75.3, then subtract 1 here. So 85.8, I'll do it here. So 85.8 divided by 75.3 gives me 1.14. 1.14, and it will bring 1 here. So minus 1 equals 1.7 into 10 power minus 4 delta T. So this is 0.14. This 0.14. So divide. I bring this one here. It will be 1.7 into 10 power minus 4 equals delta T. So I take it out. So 0.14 into 10 power 4 delta T. Okay. So what does it by 1.7, right? Okay. If I do this, 0.14 into 10 to the power 4 divided by 1.7, it gives me 823.5 is delta T. So the change in temperature is 823.5. But what is the temperature? But what is the original temperature? So what is delta T first of all? So delta T is final T1 minus initial T0. So what is T0? 27 degrees Celsius. And what is T1? So I can say the delta T is equal to T1 minus T0 was 27 degrees Celsius. It was equal to 823.5 degree Celsius. So now T1 is equal, I take it up there, then 823.5 plus 27, that will give me 850.5 degrees Celsius. So the temperature of this coil, this heating element, this nichrome heating element now is 850.5 degrees Celsius. Okay. So what has happened here? The room temperature, the resistance of the heating element was simply 75.3 ohms. Now I am applying a voltage of 230 volts across it, which results in a current of 2.68 ampere flowing. So it settles there. So it went in. So what it means is that this current went and heated this element clearly, and resistance of it increased, and we are finding the increased resistance, or the new resistance. The new resistance is this 220 by 2.68 will give you new resistance. So from 75.3 the resistance has increased to 85.8. Why would it increase? Because the temperature of the heating element has increased. Okay, and now that means you can find the new temperature, the temperature of the heating element. And how do you do that? By using this expression. You know this. The new resistance is equal to old resistance into 1 plus alpha delta T. Okay. So alpha is also given for this temperature range. Alpha is given to be 1.7 into 10 power minus 4 per degree Celsius. That's given. So 85.8 is equal to 75.3 to 1 plus 1.7 to 10 power minus 4 into delta T. So then you manipulate it, then you get the value of delta T here. What is delta T? Change in temperature. The change in temperature is so much. Then what's the temperature? So change in temperature means final temperature minus initial temperature. Initial temperature was room temperature 27 degrees Celsius. And what's the new temperature? New temperature must be the change in temperature plus the initial temperature, that gives you 850.5 degrees Celsius. So right now this heating element is at a temperature of 850.5 degree Celsius. Hope it's clear to you.